Example. IQ is normally distributed with a mean of 100 and a standard deviation of 15. What percentage of people have an IQ score? IQ score, let's go. IQ is normally distributed with a mean of 100 and a standard deviation of 15. What percentage of people have an IQ score between 85 and 125? A quick reminder, the two things we were talking about before is we were going from X to a z-score to area or probability. The other type of problems we have been dealing with is if you have an area or probability, you want to get a z-score and then you want to get a number. There are two methods of dealing with it. So how do we do problems like this? Okay. Well, if we look at this, we have two values, right? So we have this, right? We are not talking about probability and give me a border score or what score belongs to. We have scores, and we're trying to find the probability in between those scores, right? Between what percentage, right? What percentage of the area or the probability. So we are going from here to here. So we have X. First thing you need to do is find z-scores. So first z-score is what? Well, z-score is X minus mu divided by sigma. So in our case, that's 85 minus 100 divided by 15. That's our first z-score. Second z-score is for 125. And that comes out to be still value 125 minus the mean 100 divided by standard deviation. And so those are the two z-scores we have. $85 minus 100 minus 15. Minus 15 divided by 15. Negative 1. 125 minus 100. 25. 25 divided by 15. So z-score, we found the z-score. Second step of solving a problem like this is what? Yes. Yes. Absolutely yes. Must have a picture. The way I see it, you are allowed to skip breakfast and coffee, but a picture is a must. I see smiles, coffee drinkers, addicts. Okay, let's quick reminder. Why am I putting 0 here? Because I standardized the mean to be 0, right? This is standard normal curve. All right, so let's find a place for -1, say here, and a place for 1.67, let's say here. When the time comes to do homeworks and exams for this, I don't care where you actually place it. You don't have to measure it specifically, just in general vicinity of where it should be, right? Just like I don't expect all your curves to look exactly the same. All right, and now which area are we looking for? We're looking for between those two. So somewhere between here and here and this big section. Now, when we look at our table, standard normal distribution, that table only gives you the area to the left of the z-score. So, what are we reading? If it's to the left, then we're going to have to get two of them. We're going to have to get this one. How big is this area? Right here. You sure it's 14? It's 14 or 15? 15, not 14, 15. And the second one, the second area we're going to get is this one. And how big is that one? All right, let's be honest. How many of you are comfortable getting those two numbers from the table? You're comfortable? Okay. How many of you are not? You're not? Okay.
I'm just a little confused.
So you're looking for the second number, right?
Yes.
So we're looking at z-score 1.67.
Oh, okay. So
Right here, this one.
when it's a whole number, you just use 0 then?
What do you mean whole number you lose?
Like, there's no point, yada yada, for -1. So
Also, -1 is right here.
yeah. So because
1, 0, 0.
yeah. So you just
Yeah.
use 0. Okay. Thank you.
Anybody else? Are we all good with the standard normal table? Okay. So how do we get the area in the middle? This minus this. This minus this will produce this area right here, and this comes out to be, according to my notes, sorry, 8. 7, 9. Sorry?
And then we have to write a sentence.
I would like something. Right? So 39.38% of the population has an IQ score between 85 and 125. Sweet, simple, doesn't take a minute. All right, key points. So the key points that we haven't gotten so far is that z-score is a distance. What kind of distance? It tells you how far away the data value is away from the mean by counting the number of standard deviations. Area is probability, right? Standard normal distribution. We forced it to be 1 just so we can use this ability. Then we have z-score can be negative because I heard otherwise last week. No, z-scores can be negative, right? Again, that's the distance. So, but area cannot be negative. There is no negative area. Right. I know only one example of when area turns out negative. It's the United States treaties with Native Americans. They had land and now they don't. Their area turned negative. So that's the only example I heard of. We are not going to use it. Okay, so now that we have this, let's look at this. We can find data values from z-scores. Right? We got value to z-score to probability, right? And so far we did probability into a z-score, but we can find an actual value. Well, how do we do that? Well, here, if z-score is x minus mu divided by standard deviation, then if I multiply both sides by standard deviation, I get z standard deviation equals to x minus mu. And if I add mu to both sides, what do I get? Well, I get mu plus z times sigma equals to x. And suddenly, we have the last step of this travel, where we can get from probability to an actual value. Last week we did an example of weight. Weight among men there was a mean, there was standard deviation, and I wanted you to find out how many men are between certain weights. Well, today we're going to look at it from a different angle. We're going to say, hey, men's weight, and we're going to use the same mean of 172 pounds and a standard deviation of 29 pounds. That's the same thing that last time. And we know weight is normally distributed. So here's the question. What weight separates the lightest 99.5% from the heaviest 0.5%? We all read stats about obesity being a problem in the United States, about people trying to do extreme things to lose weight. So the question is, if we have population data how bad is the heaviest 0.5%? How heavy are they? Right? Lightest 99.5 means everything from the heaviest 0.5%. Which track are we on? First one or second one? We're on the second one. We are given probabilities, right? We are giving areas. So we need to find z-scores and the actual values. Okay, well, it starts the same way it always starts. With a beautiful, awe-inspiring graph or picture. A zero right in the middle. So where is this? Where is this number? If we had to place it somewhere. Where's the number that separates those two? If this is the average weight of a person, are those people lighter or heavier? And are those people lighter or heavier than the average? Yeah?
Left would be lighter and right would be heavier?
Yes, right? It's a number line. So those people, so lightest 99.5. Oh, lightest 50%, right? Somewhere here. And this is 99.5%. Right? Which means that this section right here is. Problem with percentages, our table doesn't have percentages. Our table has numbers. So this is 0.995 and this is 0.005. Right? You have to be very comfortable percentages, decimal place percentages. Okay. Cool. So what's the z-score? I love the silence. I should maybe teach statistics to my neighbors. So, we need to find in our table, in the meaty part of our table, right, we need to find this number. So we can get a z-score. So we need to find 0.995. Yes, this is the third number we're going to use a lot. And so the z-score here is 2575. I told you there are three numbers that we're going to use a lot. 1645, 1960, and 2575. So the three things that we're going to make sure we know exactly, because we're going to use them a lot. Is everybody comfortable finding this number? Okay. So you have the probability, right?
Yes.
And we know that this table gives it everything to the left.
Yes.
Right? So we're looking for the number right here. 995, 995. 995, right here.
Okay.
It's between those two numbers. We have three numbers that we're going to be using a lot.
Yes.
There was one was 1.96, which is this one, and then this is the last one.
Okay.
So it's between those two. So you just average this.
Yes.
Okay.
Got it.
Yes. It's between those two, right? 995.
Because we
Yeah.
keep looking at.
Right.
Okay, so we're doing 95.
So this is probability, z-scores are around. So if you're looking z-score to probability, you're looking z-score, then getting probability. If you have probability, you're looking for z-score, you look here, and then you go out. Any other? I'm coming. You good? I'll come back then. So probability z-scores, right? So if you have z-score, get probability, you get this, and you find it here. But we're looking for probability. So we're looking for 995. 995 is right here. There's three numbers we're going to be using a lot. Those two and this one. There are three numbers we're going to be using a lot.
Okay.
So those two we round one extra decimal place. So we take an average of those two, right?
Oh, I
So
see
it's
what you mean.
22575.
Okay.
Good, good, good. Is that maybe turning into yes?
Looking for the threes, right? So we're looking right here.
Yeah.
And then like there's another one that's like 1.
And then 196 is the third one, which is this one.
This one.
Yeah, those are the three numbers we like a lot.
On the graph, we're looking at 99.5% rather than 0.5%.
Because this table gives you probability to the left of the z-score. Is everybody okay with this? Yes? Maybe? Who throws the markers around? Such a messy person. Okay. So now we have the z-score. I'm going to put it over here. So now we have the z-score. I'm going to... We have the z-score at 2575. So how do we find the value? So x equals to mu plus z-score times sigma. What's mu? Okay, which is what? What is that? What does that stand for? In English, not in mathematics, in English. The average, right? So we go and go. The average, 172, times plus the z-score, 2575, times sigma. What is sigma?
29.
Which is the standard deviation. And our x comes out to be
That's a point, right?
yes. And the answer will be 246.675 pounds is the weight that separates the heaviest 0.5% from the rest of the population. Multiplication. Any other questions? Yes, no, maybe. Good, good, good. Excellent. Okay. All right, here comes one of my favorite questions in this little section. And this is the last example we're going to do today because I don't want to start something very, very new before Wednesday because by next Monday you're going to forget. So let's finish this. So most of the things that we use have been designed by somebody. For example, how tall are the desks? How high are the chairs? How high is this whiteboard? This whiteboard wasn't designed for me, it was designed for some average teacher about this high. Because for me, to write anything lower than here is just get uncomfortable. Same thing in the car, right? How many of you try to change radio stations while driving? You shouldn't do it, that's dangerous, but we all did it, right? You fiddle with the dials, you try to crank up the AC, turn it down, open the windows, right? All of this console has been designed to have a certain reach for you. And so manufacturing plants design cars with specific users in mind. So let's consider this. An example. There's a term called grip reach. Grip reach. And we know that the grip reach for women is normally distributed. We know that the mean is 27.0 inches. We know that with a standard deviation with a standard deviation 1.3 inches. Find the value that represents the longest 95% of women. Now I understand that for most of you and most of the questions we're going to deal with are going to be stated like this. Separate bottom from the very top. But with grip reach, right, if you have extra long arms, reaching the console won't be a problem, period. Right? But we want to accommodate almost everybody else. So we want to accommodate people that have shorter hands, or dinosaurs, right? Have you ever seen a T-Rex drive a car? No, because it won't be able to reach the controls. Let me demonstrate. Right? So if a T-Rex is driving a car, right? Right? If T-Rex is driving a car, there's no way you can reach the AC button, right? So we are not worried about T-Rexes. But we're worried about everybody else, right? I never had a problem switching things in my car, right? I can eat a hamburger, talk on my phone, and drive a stick shift while looking for something, right, in the glove compartment. I have no problem doing that. My partner, on the other, is 5 foot. She racks up the seat so close you can barely see her, right, behind the steering wheel. And changing the AC, okay, radio, okay, but if you want to do an emergency blicker because somebody was nice to you and you just want to blink them twice so they know that you appreciate them, that's for her is like one of those moments, right? So when we design cars for a specific group, and in this case we're going to design cars for women, we have to be very much aware of how long your arms are. And we want to accommodate the most amount of people, right? And it's easier to accommodate long arms rather than short arms. Thus, We want to accommodate 95% of the longest arms. So what would that look like? Well, they're normally distributed, so where would be the 95 longest? Where would you do the cutoff? Here, 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 here. Yeah?
Like the last one on the end of the right?
Here?
Yeah.
You sure?
Yes.
This is a number line, right? So this is the long, this is short, right? And we are asking for represent the longest 95%. Longest starts somewhere back there, keeps on going, 50%, 70, 80, 90. So this is the 95. This is the 5. It's okay. Sorry?
Would it make a difference if we put long, short, and then the graph is split?
Yes and no. So the question, yes, if you flip the graph, you put 0 and 95 on this side and 5% on this side, your z-score will look different, right? No, the graph is symmetric, so if you know that you're flipping it around because you want to find the z-score, and you know to flip the z-score back, right? Because it's symmetric, you can do a lot of little adjustments. The problem is most people will try to do this flipping thing around, and they will forget about one of those flips, or they will forget to adjust the sign. So it's better to be diligent on this, and then everything just falls in. Okay, so we have that. So what's the z-score? What is this magical number over here? Yes, but minus. Right, we are below 0 over here. Right? So this is the question that was asked before. 1.645 would be here, right? But you understand that this is asking you to be below the mean, so you have to put a minus. Most European textbooks for statistics give you only one of those tables. They don't give you both. They don't give you for z-scores below a 0 and above a 0. They will give you one, and you have to be able to switch it around. We have the luxury of having all of it. So, okay, we got a z-score. What's next? Well, next we're going to use, I'm going to be lazy. I'm just going to erase those two lines. I'm going to use this. Well, z-score changed. Too lazy. So what do we get? Well, mean is 27 plus z-score negative 1.645 and a standard deviation of 1.3. So we get that x equals 2 Everybody's okay so far? Good. So what's the answer? With grip reach of at least 24.86 inches, only 5% of women won't be able to reach. With grip reach of at least 24.86 inches, or grip reach distance, only 5% of women won't be able to reach. You stroll into a saloon at 4 foot 3 inches, people are going to be like, nah, this truck is not for you. And reach is one of those. There's a lot of those things that statistics accommodates. Coolness factor, right? Honda Element supposed to be designed for people which are in their 20s. Most people that buy it are men between 45 and 60. Was designed for teenagers. It's used by somebody else, right? So it's a question of, can you study your market and can you pick decisions?